Hello, my name is Stefan Hartzell. I'm a principal scientist with Automaton, and I'm excited to get to talk to you about VISTA. VISTA is a tool that we created as an open source project to support the GeoInt community to develop Python tools and capabilities and test them for visualizing and understanding GeoInt imagery. The quickest way to get started with VISTA after pip installing it or cloning the repository and adding it to your Python environment is to hit this file menu, which is in the upper left. From there, you can go down to the simulate button. From the simulate button, you can run Vista's built-in imagery simulator. This will just create a random scenario at low fidelity, which is a quick way to introduce Vista's principal features. When completed, Vista will invite you to load the simulated data into the viewer. When we hit yes here, it loads in, and what we can see is the imagery that got loaded along with other features. VISTA breaks data down into a few different layers. You have sensors. Sensors can contain multiple stacks of imagery, and then tracks, detections, and other features can be associated with that imagery. The first tab here in the data manager is the sensors tab. Here we have sensor named simulated sensor. In the imagery tab, we have our simulated stack of imagery with 100 frames. The tracks table includes our relevant tracks that are in this data set. And our detections tab has all the different detections that we have for this data. And in a minute, we'll get into more of the other features Vista has to offer. Once data is loaded, Vista allows the user to animate through sequences of image frames using either the slider or playing, which can be toggled with the spacebar button. Users can move this dial to adjust the playback speed and direction. You can also step forward and backward one frame at a time using A and D and the forward and backward keys as a shortcut. Vista also provides a few ways of customizing the view into the imagery you're looking at. The first of these is the histogram. This histogram window can be adjusted by the user by clicking and dragging to adjust the color contrast being shown based on the histogram of data. The bounds of that histogram can also be adjusted by using these handles on the left and right. The color scheme is also adjustable by clicking here to this preset gradient where users can choose perhaps either a thermal gradient or other available gradient presets. Users should note that the histogram can also be toggled off or on by clicking the histogram button here in the toolbar. I prefer black and white, so I'm going to switch it back to that. The histogram fidelity is also configurable in the settings. Specifically here on the imagery tab, one can choose how many bins are used and the automated percentile clipping, which is the default setting for the handles, as well as how much the imagery is sampled in order to produce the histogrammed imagery. That's important because computing the histogram can take some amount of time, and showing the histogram can slow down the player. Usually it's not a big factor, but especially on larger imagery, it can make a difference in terms of the playback speed. I'm going to introduce more of these toolbar buttons in a little bit, but first I want to walk through some of these features that we're looking at in this viewer. So first off, we have our tracks. The tracks are shown in the table, scrollable here. There's a lot that can be shown in this table. It can have a tracker name column, the lengths of the relevant tracks, etc. You can right click on this table to do filtering operations. So for example, if I rename this particular tracker row to tracker 1 and I filter on this, I can see all the unique values in that column, kind of like in Excel. I can filter down to just tracker 1, and that will hide the other ones from this view, which then lets me potentially manipulate this one specifically a little easier than having to manipulate all of them at once. I can clear filters to get all these back. You can manipulate particular rows by changing values on those rows specifically. You can also, using typical selection rules, so holding down Control, you can select multiple things. Holding Shift, you can select a whole group of tracks. And here at the top, there's bulk actions available. So from here, you can toggle features on all of the selected tracks. So I can toggle all the visibilities of all the tracks that I have selected. I can change their color, make them all blue. I could also change the marker type. So for example, make the markers all diamonds. Um, you can change the line style. So I could make the line a little wider. I could make it shorter or more narrow, I should say. I can also change what type of line we have. And all this is to help with distinguishing different types of tracks. In my own work, I've often had multiple trackers loaded, and I'll typically select a grouping of a specific tracker and then change its color all at once to a particular color of interest for my work to make it easier to distinguish different trackers from each other. Now, one of my favorite features personally about Vista is the undo button. So you can undo actions that you've taken on both the tracks and detections tabs here in the data manager. So just pressing Control Z, I can undo a configurable amount of actions. The amount of undos that are available are configurable in the data manager in the Vista settings. So I have my undo depth set to 10. So that's the furthest back that I can undo actions. Undos can also be done in addition to Control C or Command Z by pressing the undo button over here. Another common use case for Vista is to do labeling. So this could be for machine learning purposes or just to annotate a data set that one has loaded. So I could select a few of these tracks, for instance. I can click this label selected button, and this would allow me then to label these. So I could say that these are truth tracks, for example, and that will add that label into the labels column. And if I were to export these tracks later on, that label will be preserved. Another fairly new feature in Vista is the ability to extract target signal by choosing particular pixels that are believed to be part of the target signal. To do this, a user should select a particular track, and from here you can click the extract button. This will give the user the opportunity to try to automatically extract these signal pixels. This uses a constant false alarm rate detector effectively in the area around where the target is reported. In doing the extraction methodology might want to update the center of the target as it sees it. That's what this enables, this checkbox down here. I'm going to leave this on for the time being. And there's a maximum that you might allow the automated shifting to support. And there's more details on CFAR in the full-blown documentation. I'm not going to get into it too much here. But if I go ahead and click run, then it's going to try to automatically determine which pixels are part of the target signal. As you might have seen, some of our track points got updated because we allowed it to do so by leaving this checked. From here, we can move forward and backward in frame. Often I do this using the hotkeys A and D, and I can see which pixels were selected as part of the signal. We'll also see here that populated this average SNR column. I can move that column a little closer to the center to make it easier to see here by dragging and dropping the column. And from here, I can also adjust the extraction if I wish to by clicking this Edit Extraction button. When I click the Edit Extraction button, you get presented with a menu where you can try to automatically update the pixels that it has identified on this frame, again using CFAR, where you can adjust its particular settings. If you hover over these options, it will explain what these are. But of course, there's no substitute for the full-blown documentation on CFAR. And there's another view I'll show later in the detector that actually visualizes what all these settings are doing. But in addition to that, users can manually click on particular points to add them to the signal. Whether you want clicking to add a pixel or remove it is determined by this toggle. So I can remove pixels by changing this radio button to the clear setting. If I move it back to add, I can add pixels. Users can also change the brush size. So I can, for example, add a grouping of 4 at a time, which is almost certainly excessive. So here I can remove a few and then put some more back. If you need to add a whole lot at a single time, you can lock, pan, and zoom. That enables dragging to select a bunch of points. That's an easy way to grab points quickly. The reason you have to lock the pan and zoom is because otherwise clicking and dragging would typically pan the view that you have. When you're happy with the extraction, you can dismiss it by clicking Save Changes or just exiting out. You can also rearrange columns in this table. It's just something I want to highlight real quick. Let me adjust some names here so it's easier to see, but you can grab groupings of tracks and drag and drop to rearrange elements in this view. Next up, I want to introduce detections. So detections are seen on the detections tab, and one row in here corresponds to a particular detector or detection group. As we animate through frames, we'll see these red circles pop in and out. Those are detections. So they're not correlated across time like a track. They're just on a particular frame at a particular location. This detector believes there is signal present. If one wishes, you can view all the detections across time by clicking complete. That can be handy because you can sometimes make out tracks just from that. Additionally, users can take other actions in the detector, such as changing its name and also changing its style. So kind of like tracks, you can click on these cells and update particular things about the detection. So here, maybe I'll make this more like pink, and I can change the marker size, and I can change the marker thickness. All right, so now I think I want to introduce some of the other toolbar features. So I'm actually going to go ahead and delete my detections, delete my tracks. Again, if I wanted to get those back, I could do Control Z, get them all back. But I do in fact want to delete them. You can also delete selected items on the tracks and detections pages, as well as sensors and imagery by pressing just the delete key in addition to delete selected, just FYI. All right, and from here, I want to manually track these objects. So to do manual tracking, you click this button on the toolbar, create a track by clicking on frames. When you have this selected, the status menu down here tries to give you some instruction on how to do this, but there are 3 modes for how it will try to track objects through this scene. Verbatim is the simplest to understand. It simply selects exactly where you click. So I'm clicking here to say that this is the start of a track. I can step forward a frame or two and click again, click again, click again, and get more track points. If I have peak selected, this setting immediately comes into effect. And what will happen is it will try to look for the peak signal pixel closest to where I click. And that is configurable. You can look for signal that is either exceptionally dark, so it'll look for more so negative pixels, or bright, or both. I have it set to both at present. And now it's going to pick pretty much right in the middle of this signal, even if I'm a little bit off from where it is. CFAR runs a localized detector around where you're clicking to try to find the weighted centroid of a blob of connected pixels. So using that setting, I can again click pretty close to the object, and it will generally find the right one and get us close to the weighted centroid. When I'm satisfied with the track I've produced, or if I want to edit, I can also click on a point on a given frame, make it disappear, click again, reset it. But when I'm satisfied, you can uncheck this toggle button, and that will then complete the track. Now, as you might note, we didn't make we didn't call out track points on every frame. So there's some gaps here that then get filled in when we get to those track points. We can fill in missing gaps like this by selecting the track or multiple tracks and going to track filters. And there's a couple options. You can run either Savitsky Golay, which will produce a much nicer, smooth track interpolating points, or just a regular track interpolator. So here I'm just going to use a quadratic interpolant, although you can choose a few different ones, linear, cubic, nearest, etc. If you use quadratic, I'll run this, and it inferred the location of the other 24 track points. So here, now we have track points on every frame between when we started and when we finished the track. I'm going to delete this track and show how we can also do something similar with detections. So clicking this toggle button, we can click detections. We have the same options as when we create a track. I'm just going to do verbatim here for simplicity, and I could create detections on multiple frames like this. And this isn't making tracks per se, it's just making uncorrelated detections. When I click it again, that detector is finished. We'll see here in the detector or detections panel, we see a new detector. If I hit complete, I can see all my detections across time. And if I navigate back those pixels, I can see the detections that I created just by clicking in the viewer. The next toolbar feature I want to introduce is this hover tool. When you click on this, it enables a tool that shows the row, column, and counts of your hovered pixel. So if I zoom up real close, we'll see it only changes here as I move into a new pixel. And you can configure the styling of this hover tool in the settings. So if you go here to settings, we could make it green, and we could change, for example, the font. We could change the font weight. And now we get a different style. It can just make it easier to see for some folks. I prefer the yellow, so I'll go ahead and move it back. I'll just use this preset. And yeah, 12. I think that's what that's what I tend to prefer for myself. And then I want to introduce these selection tools. So in order to show that off, I'm actually going to delete our detections that we created, and I'm going to run our first algorithm. So VISTA comes out of the box with a few different algorithms. They vary in quality. The detectors are pretty good. The background suppression is pretty good. The trackers are fairly mediocre. These algorithms were put in place more so to illustrate how one would do certain algorithms in this tool. Algorithms are often specific to a sensor or phenomenology. So these are really just illustrating different categories of algorithms one might want to use. But the CFAR algorithm is pretty decent. So here I can choose my processing region. I want to run on the whole imagery. I'll show a little later how we can run on a subset of the imagery. And what this does is it basically evaluates every pixel looking in the neighborhood around it. So it looks at this test pixel. It ignores the pixels that are blocked off in white, which are defined by this ignore radius. And then it looks in this kind of donut, this square annulus around that test pixel to try to get an estimate of the local noise around the test pixel. And if the pixel under evaluation is a certain number of standard deviations, 3.5 in this case, above its local background, then that pixel is flagged as signal. And groupings of signal are coalesced using connected components, and only groupings larger than 4 in my case and smaller than 1,000 are retained. Again, we can look for things that are either bright or dark or both. If we want, here we're going to look for just things that are bright. We can also use a true donut, a circular annulus. It's a little bit slower, but it can provide a little bit of improved performance in some cases. In this case, I'm going to go ahead and run the square annulus, run our detector, and it found us 339 detections, and it should be pretty much on the money for finding our targets. And indeed it is. So from this point, we can do a few things. We can make tracks out of these. So what we can do here is select this tool. This is a tool that lets us click on detections in the viewer. And as we click on these, it'll remember what we have selected. So I'll kind of make a track manually here. There's a faster way, which I'll show in a bit, but just kind of want to illustrate this. And here on this detections tab, now we can click create track, and that will create a track out of our selected detections. So that's the nature of this tool here. We could actually do it faster if we wanted by showing our complete detections. And now what I'm going to do is I can, for example, use this lasso tool, and I can grab all my detections that are over here, and I'm going to create a track out of those. And we should now have another track. There we go. And I'm going to grab another grouping here, create another track, and then I can get these missing points here by clicking on them like this. I'll make another track. And now I have 3 tracks, and this is going to give us an opportunity to highlight 2 different tools. One is this tool here. This lets us click just on the viewer itself to select particular tracks. By default, click will change selection, but if you hold either the Command key on Mac or Control on a Windows machine, you can select multiple tracks. So I'm going to hold Control. As you can see, they're toggled off as well here in the table as I change my selection. So when I have these three selected now, I can now merge these tracks. So I'm going to go ahead and merge them, and now I have a completed track. I am going to go back and show another feature that I think we missed last time. If I select this track, I'm going to go ahead and do an extraction. Again, this tries to figure out how much signal is on every frame. I'm going to close that out. And one of the things this will let us highlight is you can also click this plot track details button. This will pull up a plot that is synchronized to the data you're looking at. We can see here it's changing the zoom because it's incrementing as we go back and forward in data. If we show complete plot, it'll instead show all the data across time and just highlight our current point. Looking at frame and row isn't quite so interesting, but we can look at frame versus the signal total. And now we can see how our signal changes over time. In this case, it's not particularly interesting, but this can be a very useful way of looking at the data. This tool also includes a symmetric logarithmic plot, which on this data doesn't produce the best view, I'll say. So I'll go ahead and toggle that off. But especially on data with a large range, that can be quite useful. You can also turn on a legend to see the colors that belong to the different points. And if you hover over the track in the status bar at the bottom, you can see that it actually gives the name of the track that you are looking at here. I should also point out you can add multiple tracks here as well. Only one of these is extracted, so it's not showing up on the signal view, but if I change back to looking at, say, frame versus row, now we can see both our tracks and we can animate with both of them. So whatever you have selected in the table synchronizes to what's shown in this plot. And you can have multiple of these plots open as well, which could get our screen real estate a little busy, but just want to make sure that users know that that is something they can do. You can also export data out of these plots, just the particular axes you have shown, and you can also export a plot image out of this plot details view. Now I'd like to show some data that's a little bit more realistic than what you get out of this built-in simulate function that is really, really quick. Vista's documentation covers this, but Vista also has a few Python scripts in the scripts folder to generate data that actually has a background. It's a little bit more representative of the situations you may be interested in. So I've gone ahead and simulated some data here. I'm going to go ahead and load it. And as we see, we have a background. It's a little bit shaky. The sensor's not perfectly registered, and we can kind of make out these little blobs moving around in the scene. So if we wanted to pick these out and create tracks out of them, there's a few things we can do. Firstly, one might often want to do treatment steps, so bias removal and non-uniformity correction. Vista provides these as an example of how one would implement this for their sensor, but typically treatments are very sensor specific, so these are mostly provided as an example. So I'm going to move past that and move on to background removal. So this will try to estimate the background in this imagery and remove it. So I have a few options for what I can do to remove the background. But before I do this, I want them to run pretty quickly. So I'm going to focus on an area of interest. So I clicked this button in the toolbar here to create an area of interest. And I can move it around by clicking and dragging. I can adjust its size by clicking here in the corner. So I'm going to make our area of interest box. I can give it a name, and it will update in the view. Also, as I adjust its size, its bounds update in the table. An issue that some users have is they want to pan around in an area, but when they try to do so, it moves the area of interest. The way you can get around that is you can deselect the area of interest by holding Control or Command and clicking this table row, and it'll be deselected. So now it's not moving around when we try to pan. Pretty much all the table selection is done through clicking on entire rows in Vista. So now if I have it selected, it moves around. So now we can run image processing specifically on this area. So if I hover under background removal, I'm going to do GoDex. This is Go decomposition. I'm going to select our particular area of interest to run on. And we can either add the background imagery to the viewer, or we can add the foreground. We're interested in the foreground. That's where our target signal should be. And this is a GPU-enabled algorithm. So if you do have a GPU and PyTorch installed with VISTA, you'll be able to take advantage of that for accelerated processing. So we'll go ahead and run this on our area of interest. And there we go. It went ahead and processed the data. At this point, I don't need that area of interest anymore, so I'm going to go ahead and delete it. And we can see our objects a lot more clearly than we could before. And we can toggle between our original imagery. It wasn't lost. It's here. If we click that, then we can see the original imagery just as it was. If we click this, our area of interest, background suppressed imagery, goes in the area where it should go relative to the original. So it has the row column offset information remembered and all of that. And we can see our target signal in here moving around. And you can, as you see here, you can see the device, the GPU device that this imagery is on. So it moved it to my RTX 3090. You can configure what device is used here under the settings. If you go to GPU, the GPU tab, you can see the different devices you can choose from. I only have one graphics card, so that's all I can pick. And you can move data off of your GPU to release that memory, or you can move it on preemptively to accelerate image processing steps that can take advantage of the GPU. And from here, we can run some of our algorithms, such as detectors. So we can run that CFAR algorithm just on the whole image that we have selected. So when this says full image, that full image is relative to our selection, so which is already cropped. So this is going to just process this thing that we're looking at here. The way CFAR works is it looks at each of these pixels and it evaluates how bright or dark they are relative to the neighborhood, which is represented by this kind of blue colored annulus around the test pixel. And we can make the annulus circular like a true donut if we want. It's a little faster square, but you can get slightly better performance sometimes if you pick circular. If I were to go ahead and run this, it will take a few seconds, but then we should get pretty good detections on our target, or I should say on our targets. All right, so it finished running. We can animate through here and see that we're getting detections on our targets. We're also getting a lot of false detections along that poorly registered coastline and so forth, residual clutter coming out here through the background suppression. And if we wanted to turn on our complete detections, we can pretty clearly see our target paths coming out here in addition to a bunch of clutter. So that kind of shows a use case you might have from here. You might want to manually track. You might want to run some of the auto trackers. It's up to the user how they want to proceed from here. And then perhaps they want to export that data and look at them in another tool or incorporate them in a report. And as I said, we can always get back to our original imagery, and we can deselect our detections if we want, or view them over time relative to the raw imagery as well. All the tracks and detections are attached to the sensor you have selected. So regardless of what imagery you have picked, it will show all those features. Something else I want to introduce users to is the ability to add features to the view. This data has geospatial metadata that's indicated by this check mark here under the geolocation column in the sensors tab. And it also has sensor times. That's why we see this time populated by comparison to the kind of canned simulated data without a background that we saw earlier. So as we animate here, we can actually see time unfold as well. And there's a few things we can do when we have time and when we have geolocated data. One of those is we can toggle on this toolbar tool, and that will show you the latitude longitude that corresponds to the values you're hovering over. Folks who know the world will know that those latitudes and longitudes do not correspond to where this data actually is in the world. Vista's built-in simulation capability just kind of picks some random data in the world to simulate and puts it somewhere. So that is not intended to be realistic, but on real data, this would show the latitude and longitude of the pixels you're hovering over. And users can also load shapefiles. So here, this just shows a couple examples of different kind of shapes that can be loaded. So these are loaded using latitude, longitude, um, vertices to create those shapes. Users can also create place marks through Vista itself. So we could create one here. If I remember those numbers, this would be about here. There we go. So we can create a place mark. We should be able to change its name and so forth. So, and if we turned on this geospatial view, it's going to put this in the context of the world. We're going to introduce that more in a minute with some data that actually is orthorectified and approximately where it should be in the world. So I'll save that for later. But I wanted to show how users can add and manipulate these kind of features as well. I'm going to delete these now from the view. All right, so next I want to show some data that is actually orthorectified realistically in the world. This is using some canned data from an in-house imagery simulator that we have at Automaton. So first I'm going to delete this scenario, and then I'm going to load in some new data. Here we go. Just going to load in this example. And in this example, this simulates kind of a MEO satellite that's observing some event happening. And we can see the perspective in this happening. Now, it can be really useful for a lot of reasons to be able to look at this in its full geospatial context. So for that reason, when you do have imagery loaded that can support geolocation, which will be indicated under the Sensors tab with this little checkbox under geolocation. When you have such data, you can load uh, you can load imagery and view it with a web map tile server. So we'll click this button here, and this will toggle on a web map tile server. We can see it's fetching tiles here to populate the background from our tile source. We can zoom out, zoom in, give it a second. Okay, here, and yeah, we can see it improving the quality when we zoom in and zoom out. And what's happening kind of behind the scenes here is our imagery is actually getting tiled as well and projected onto the WMTS. And here we can do our same actions. We can move this forward and backward in time. It animates fairly quickly, and once it has animated data, it's tiling and caching those tiles. So once we loop through this once, the next run through will go a lot faster. So here, if I start back at this point, these are frames we've already gone through, and yeah, we can see it's running, it's able to run about 20 to 30 FPS faster now. And yeah, it's slowing down now as it's caching these new rasters that it hasn't seen before. And when it loops back around, it should go pretty quick. Yeah, there we go. So this allows us to view our data with a map. You can adjust the settings here. In the settings menu, if you go to the map view, you can choose the particular tile server that you wish to use and its EPSG format as well. Storing the tiles can take a lot of memory potentially, especially if you have very large imagery. The amount of tiles that you want to cache, both for the web map tile server and for your imagery, is configurable here. Furthermore, the back projection of this imagery can be time consuming. So there's an option to use a coarse grid, which is what I'm using. This does a reasonable job preserving geolocation accuracy, but if you want the absolute best geolocation accuracy, you can turn that off. It will just take longer to project your frames, quite a bit longer depending on the size of your imagery, but it'll give you improved geolocation. It's also important to note that features also carry forward into this view. So for example, if I wanted to create a track here on this target, I can go ahead and animate a few frames here, make my track. This guy is kind of slow. I probably should have picked the other one, but oh well. here we go. Yeah, and then I think it disappears at that point. All right. So now I finished my track. Again, I can select that track and I'm gonna go ahead and interpolate 318 more points. So it's a much smoother track. And then I can go back in that geospatial view and I can view my track in there. Now we can see here, probably because of my coarse geolocation sampling, the geolocation in this view isn't quite on target. The target's off from where it got projected a little bit. It just depends on the accuracy of the geolocation model. This data is pretty rudimentary, but it just provides an example of being able to view data in that geospatial context. You can also create a track in this view. So here, if I try to select a few points, yeah, we can see them move around a little bit just due to the geolocation and accuracy in the simulation. And if we toggle views, we'll still see those points in those relevant views. And we can complete the track if we wished. We could finish it up in one space or the other. So there we go. Our track is complete over here. And that sums up the principal features of VISTA. We invite you to explore the tool for yourself. We hope that you find it useful and that it accelerates your GeoEnt development. We've been using it for a lot of our own purposes, especially machine learning labeling and just getting a sense of the data we're looking at and being able to integrate R&D algorithms and make them useful to people faster. So we hope that you are able to find this useful as well. And yeah, thank you for your time checking out VISTA with me.